Hi everyone, my name is Sergio Dorado-Rojas and this presentation is called Low-Cost Hardware Platform for Testing Machine Learning-Based Edge-Powered Grid Oscillation Detectors. This work was developed by myself, Shunyao Shu, Galileo Olvera, and directed by Dr. Luigi Vanfretti at Rensselaer Polytechnic Institute. This presentation is structured as follows. First of all, I will give some motivation in the context of modern power systems. Then I will briefly describe how meaningful signals can be generated using our proposed approach. Briefly, afterwards we will discuss what the algorithm was used for oscillation detection, and finally we will jump into the proposed hardware platform, describing each of the components that were used for oscillation detection and how they communicate with each other. We will underline an important point that is related to the analog to digital converter selection and how this impacts the performance in terms of accuracy of the given of any classifier. And finally, we will conclude our presentation by stating the main conclusions and takeaways of the work. So let's get started by giving some context and motivation for this work. So worldwide, we have seen that many governments have introduced heavy investments to modernize the electric grid. So they want to make the grid more greener by exploiting as much as possible renewable resources, non-conventional renewable resources such as solar energy and wind energy. So the main issue for the grid is that these resources interface with the bulk electric systems through converter-based devices. So the problem is that they introduce new fast dynamics, and this can result in unwanted interaction between their controllers and the controllers of conventional plants. This phenomenon is known as forced oscillation in power grids, and here we have an example. In this case, a PV plant is introducing an undesired 8 Hz oscillation to the main system while it generates power. So the problem with these oscillations is that they have to be detected on time so that remedial actions can be taken to reduce their negative impact on the system. Conventionally, this is done by complex signal processing algorithms that have a remarkable computational burden. So if we were to prioritize the computational efficiency of detection methods, we could have an eye on machine learning techniques, especially deep learning methods that emerge as data-driven solutions that once or after being trained, they could be deployed efficiently on computational pipelines, mainly because they are mostly a series of sequential linear algebra operations that nowadays have been greatly optimized. So let's at this point assume that we have an existing deep learning solution that we want to validate in real time. So how do we do it? The answer from a power system engineer perspective would be that we generate using a model of the system or using some historical data. We can stream using a real-time simulator that historical data or the result of a model simulation we just connected from the real-time simulator to the device where our neural network has been deployed. However, real-time simulators are really expensive. So and moreover, in some cases they can only be accessed in place. So that was a problem that our group experienced during COVID, that we couldn't access the facilities, so we couldn't perform real-time tests, and we wanted an alternative that was, on the one hand, low cost, and on the other hand, that could be accessible anywhere. So we proposed the following platform that consists of a signal generator, an analog to digital converter, and a NVIDIA Jetson TX GPU device that is CUDA capable, and a laptop. So this is a low-cost hardware platform because these two devices are not really expensive. In fact, this signal generator is used in basic introductory electronics courses at the undergrad level in our institution, and this GPU can be easily achieved for, can be purchased for less than $500 in the market. So this interconnection constitutes a platform that can be used, as we will see later, for validating the real-time performance of a deep learning-based oscillation detection algorithm, but can be expanded to validate other functions, as we will state later. So first of all, let's jump into the context of oscillation detection. So I would like to describe briefly how a simple signal can represent an oscillating condition. And let's start here by underlining that in an equilibrium condition, so power systems try to operate in an equilibrium condition, we have no evolution of the dynamics. So either we have that our system is operating at an equilibrium point or at an equilibrium trajectory. What happens is that loads, conventionally loads, but nowadays also renewable resources, are changing all the time. This means that our state is not locked at an equilibrium trajectory or at an equilibrium point, but rather it is oscillating a little bit around such a equilibrium lock. And this means that if we were to generate a signal representing an actual oscillation event, we need to have some oscillations around a constant value or trajectory, as shown here, and then an abrupt change in amplitude, as depicted here. So this is the most basic signal that we can use for inference. It's a really simple signal, but it has a lot of meaning, as I have seen before. And a point worth underlining here is that the signal is easily, this noise can be really injected in a straightforward manner using a signal generator. So now let's briefly discuss the algorithm that we employed for oscillation detection. So the algorithm is a one-dimensional convolutional neural network that was trained offline. So here on the left we observe the architecture of our network, and on the right some training results. But unfortunately the deeper discussion on the model selection and model details is out of the scope of this presentation, so we encourage you to check the paper where we dive deep into the details of this proposal. So now let's go back to the hardware platform. So here we have a more clear diagram. So first of all, we generate such a signal as simple as the one that we have discussed before, using a low current, low voltage generator, as this one shown here. So this particular generator, this discovery board, comes with a Python interface that can be used to automate waveform generation. Then the analog signal generated by this device needs to be transmitted to the NVIDIA Jetson, but the NVIDIA Jetson has digital inputs. So we need to convert this analog signal to a digital representation, and we do that through an ADC. So we tested two different ADCs, an 8-bit and a 16-bit variant. We will see the impact on performance of the ADC resolution later. And finally, the offline trained model was deployed on a Jetson device that carries out the inference as shown here. So the deployment process is conceptually simple. So we have the weights from our offline trained model. We export them to a format that is that has the PV extension, and we optimize these weights for real-time execution using TensorRT. Once the model has been optimized, we deploy the trained model to the target, and then the target is capable of receiving the inputs and performing in real time an inference result. So here I would like to underline that this platform can be used for more than machine or deep learning algorithms, because this NVIDIA Jetson device is CUDA capable, and CUDA has nowadays several libraries that enable, for example, the efficient execution of signal processing algorithms that could be used, for example, to evaluate protective relay functions in power grids. So now we have seen here in this slide how everything is interconnected, but actually the communication is not as straightforward. So here we see the different protocols and the ways in which each device is talking to the others. And then here on the right, we observe the flowchart that represents the actions from when the experiment starts to when the experiment ends. So not to spend a lot of time on this slide, basically what we are trying to do with this flowchart is to guarantee that a new signal is not being sent until inference has been completed here. So that is more or less, we want to give the NVIDIA enough time to complete the inference given one batch of the input signal, more or less. So now let's analyze the selection of the ADC. As we mentioned before, we work with two different variants with different resolution, 8 and 16-bit, and we observe in this slide the different results. So we observe that for low frequencies, that, well, in all cases, we see that the performance in terms of accuracy of the 8-bit ADC is lower than the one for the 16-bit ADC, but it downgrades really fast here at this point. So there is a point where the bandwidth of the ADC is no longer enough for the frequency of the signal. So that happens here for the 16-bit ADC. But if we're interested, for example, in just evaluating modes from 0 to 20 Hertz, then the 16-bit ADC should be okay. Here on the right, we can see that the accuracy of the 16-bit ADC is concentrated more towards, or is skewed towards the 100% accuracy, which speaks really highly of the network that we developed, and it makes more or less sense because we developed the network for real-world oscillation profiles, and in our tests we included just one harmonic for demonstration. Meanwhile, the performance of the 8-bit ADC is more distributed, and we see some hits. I mean, everything is above 90%, but it's not as concentrated towards the 100% accuracy as in the other case. So we conclude that the performance of both ADCs is similar for low frequencies, but as we increase and we approach the bandwidth of the ADCs, then the performance downgrades. So thanks to this experimentation, we can state that adequate ADC selection is a critical part for the design and implementation of a machine learning or deep learning based classifier in power grids. So we jump here to the conclusions of our work. So we have introduced a low-cost platform consisting of a signal generator, an ADC converter, a laptop to coordinate everything, and an NVIDIA Jetson GPU. We demonstrated this platform in a simple application that was the detection of subsynchronous force oscillation in power grids. So here you have a more realistic pattern that was extracted from our other paper, but this is the kind of signal that we can actually generate using the signal generator programmatically. And then beyond teaching, demonstration, and what we have shown, that is validation of machine learning solutions, this platform can be also used for real-time or time-critic signal processing applications, where the CUDA library is employed here in the Jetson GPU. And finally, we have quantitatively shown that the selection of the ADC can impact positively or negatively the performance of a machine learning algorithm. So that has been it for this presentation. Thank you so much for your time, and feel free to reach out by email if you have any questions.